please.
Thank you. Yeah, thank you very much. Thank you for coming back. And so today's topic is the cyclotomic USL theory for elliptic curves. And let me first explain why I do this. So basically, the main object of this cyclotomic USL theory is one is the periodic L functions. And the other part is Selma groups. And they are connected by the main conjecture, USL main conjecture. And so what's the role of the Euler system, especially Kato's Euler system here, is the following. So Kato's Euler system. To the algebraic side, we derive the Kato's Kolyvagin systems. And bound Selma group. On the other side, there exists so-called Kalman map to obtain periodic L functions. And another way to obtain the periodic L function is to use the modular symbols. And directly from modular symbol, we can construct the periodic L function. And of course, these modular symbols and Kato's Euler system coming from the one a fixed elliptic curve or modular form. And so in mind, from the point of view of motifs, so I want to regard as the Kato's Euler system is a kind of étal one, corresponding to étal realization of motifs. And modular symbol, it can be regarded as a Betti realization. So, and also, there is a connection from the Kato's Euler system to modular symbols via dual exponential map. Indeed, the Kalman map is the interpolating this dual exponential map. And why do we try to make the connection between Kato's Euler system and modular symbols? And a very good advantage of modular symbols are very computable. So modular symbols. And so how can I say that? It's the analytic and computable. Incarnation of zeta elements. Very lovely. So yeah, in fact, the L function is directly related to modular symbols. We will see that. And one may ask, not necessarily one motive. It's just the philosophical thing. So I want to match up various realization of motives and the various construction of periodic L functions. That kind of analogy. And so one may ask, then what's the drum thing? Drum realization. And in fact, there is another construction using Rankin-Selberg method, but we will not discuss in this lecture series. And the big chunk of this lecture will focus on the modular symbols and the construction of the periodic L functions. Okay, so periodic L functions and modular symbols. That's the construction. So, okay, what's the L values? So where does it come from? And for a given elliptic curve over Q and using the modularity theorem, we have the corresponding cusp form. This has the following Q expansion. And level is same as the conductor elliptic curve, weight is 2, and all Fourier coefficients lie in integer. And the L function is nothing but this Dirichlet series with coefficient with an. And so what I want to do now is try to motivate the modular symbols. So how to do that is we want to express L values in terms of integrals. And in all the computation from now, I will ignore every conversion issue. Then let me start with the gamma. Let me recall the gamma function. It's nothing but integral from 0 to infinity, e to the negative x times x to the s minus 1 dx. And by change of the variable, then do the same as 2 pi I to the s times 0 to infinity, e to the negative 2 pi n x times x s minus 1 times dx. And multiply L function and gamma function. Then this is nothing but just formally write down, we have this. And now, yeah, as I said, I ignore all the conversion issues. Just freely change the order of the infinite sum and integral. Then I have the integral of the sum of an times 2 pi n x times x to the s minus 1 dx. And this is nothing but f of ix. Then sending s to 1, then what do I have? The L value is nothing but 2 pi times 0 to infinity. It's f of iy dy. Is another way to say this, 2 pi I times the integral from I infinity 0 f z dz. Okay, it gives you kind of the motivation.
Sorry, Chanu, you're missing a 2 pi I in this.
Where?
On to third, fourth line. What happened to the I?
Let me see. Did I think it's okay. Yes.
No, there's a 2 pi outside. And inside, what happened to the minus? Why has it suddenly become a e to the power 2 pi nx? And what happened to the denominator?
I'm a little bit confused. Let me see.
No, the third line, you have this
right.
denominator, right?
Yeah, I think I checked this and it shouldn't be a big problem. Yeah.
Okay.
Yeah. Okay, let me first go with this, and it's such a like a constant factor should be like a checked easily. Yeah. Anyway, what I want to emphasize is that this L value can be written as the integral of the modular form, like this. And we also need to discuss the twist. And let me consider the Dirichlet character chi from the Zima DZ cross to C cross.
The second one, shouldn't the integral be from 0 to I infinity?
Sorry?
This integral, 2 pi I,
Yes.
the bounds are from 0 to I infinity or from I infinity to 0?
Oh, this is okay. Like if you like do the change of variable, the sign change appear.
Okay.
Yeah. Okay. Dirichlet character of conductor D with the D is coprime to the conductor of the elliptic curve. Then how can we express the L of E chi 1? And then I need to introduce some Gauss sums. So tau and chi is sum over A runs over Zima DZ cross, and chi A times e to the 2 pi I n times A over D. Okay, then if we put n equals 1, then we get the usual Gauss sum. What's the point in the 2 pi I n? And I think it's okay. Yeah. That cancels in there. Okay, the Gauss sum. And tau and chi is from these two, we have the chi n and take the complex conjugate times tau chi. Then we consider the twisted modular form, twisted by chi bar, that f chi bar of z is the sum, can be written as follows. So it's the following twisted modular form, an e to the 2 pi I and z. And rewriting this Gauss sum using the tau and chi, then I have the 1 over tau chi times sum of tau and chi times an times e to the 2 pi I and z. And rewriting again, 1 over tau chi, the same sum, but now I decompose using, sorry, it's using the character chi. So sum runs over A, Zima DZ cross, and chi A times AN, and e to the 2 pi I, and Z plus A over D. Then using Birch's lemma, you can find the statement in the paper of Major Tate Teitelbaum. then we get the following the integral form. So LE chi bar 1 is same as the 2 pi I tau chi, and sum runs over the A lies in here, the Zima dz cross times integral A over D I infinity f z dz. Here, tacitly I use the symmetry of modular form. This is used. So f of z plus 1 is f of z. And another way to say this is the following. So just replacing the Gauss sum by the different character is the inverse character. 2 pi I sum of chi A runs over the same group. Sorry, times here the variable is changed, is multiplied -1, something like this. Okay. Oh, sorry. So all these computation leads to the following notion. This is what I want to say. These computations lead to the following notion. So first I write the modular form is modular curve is complex points as the quotient of upper plane by the gamma naught n, of course, adding the cusps. And for a given two cusps, I define the following integral for pair alpha beta in P1Q alpha beta f. This pairing is 2 pi I beta, so integral from alpha to beta of fz dz. Okay, this is so-called the modular symbols, but without any normalization. So I would write like unnormalized modular symbols. This is a notion of modular symbol for the first time. Then from these elements, we want to construct some elements in the group ring, remembering all the twisted L values. Modular elements. Of major and Tate. Is the following. So let me first fix an isomorphism. So Zima dz cross to the Gauss group of Q joining zeta d over Q. And this isomorphism, and A will goes to sigma A, sending zeta d to the A. And considering the Dirichlet character, chi, as we've seen, then by using this isomorphism, we can linearly extend the map from the group ring of Gauss group to C. then yeah, evaluation, of course, they suffice to C just goes to C linear map, and yeah, any element sigma goes to chi sigma, of course. Then the following elements will recover all the L values. So let me consider the following element. A runs over, of course, all these elements, Z mod DZ cross. And if you evaluate this guy at chi, then this is nothing but this L value. And so this element can be regarded as an unnormalized major Tate element. The modular element, whatever, is the major Tate element. And this guy, by looking at this, like this guy knows the twisted L values. And from this, like all this computation, we have some hint on periodic functions. So in this part, I will only consider the tertiary character of p power conductor. Then the z mod p to the n z cross to c cross. Then LE chi bar 1 is 2 pi I over tau chi, the Gauss sum, and sum runs over A, z p to the z mod p to the n z cross and chi a, and the integral is so I infinity to a over pn and f z dz. And one observe that like this sum very looks like a Riemann sum. In the following sense. So it's like a ZP cross can be decomposed by, so you know all the periodic stuff is totally disconnected. So we can write down like this: a plus p and ZP. And if I regard chi as like a locally constant function on GP cross, then this is nothing but the periodic integration. So as a locally constant function on ZP cross, then yeah, this gives you the notion of the periodic integration. And more precisely, like we will see the distribution relation also, but which requires the Heck action. Now I will move to the normalization of the modular symbols. Normalization. And for convenience, like I will ignore the I infinity in the notation. So write just R F is the I infinity R for r in the cusp. And we symmetrize the integral. Then the RF and plus minus is 2 pi I. It's integral from I infinity to R fz dz, and plus minus corresponding to sign. Here, the integral from I infinity to negative R fz dz. And the theorem of Shimura is this guy is very algebraic. I mean, like a algebraic up to certain periods, and there is certain periods. F is the corresponding modular form. Yeah, we already used that. Sorry. Yeah, okay. This omega f plus minus is indeed non-zero complex numbers such that this integral, symmetrized integral, lies in quadjoining all the Fourier coefficients. So in the case of elliptic curve, it's nothing but just q times this period. So we have the following. So we can normalize as follows. So write the bracket R plus minus is just divide this integral by this period. And this guy lies in the Hecke field. And yeah, we can embed this into like a QP bar, and we can do some periodic theory like that. And anyway, what I want to say is in Q bar, and this is in general finite over Q. And just the bracket RF is the sum of these two. Okay, and another thing I want to point out is the following. So I should say this. So before the normalization, sorry, how can I say this? I'm sorry, okay. So let me explain a little bit of the Hecke action and the distribution relation. So on the homology of modular curves. So I regard this alpha to beta as a cycle in the modular curve. So just considering this cycle in the modular curve, and of course alpha and beta lies in the cusps. And this element satisfying the following Hecke relation. So that this type of form you've already seen in the Francesca's lecture for prime L, not dividing the conductor. Then if you apply TL to this cycle, then you will get the L alpha, L beta plus the sum runs over R from 0 to L minus 1, and alpha plus R over L, beta plus R over L. Okay, you get this. And So in fact, in order to really have the Riemann sum relation, especially when L equals P, we want to remove this part because this one really gives some distribution relation. So want to remove. So L is P here. So alpha, P alpha, P beta in the sum to obtain the Riemann sum relation. Really Riemann sum. Then we will see like there we need to do some message to the modular from F. This is so-called the P stabilization. Yes, it should appear. And like in Maishi's talk, like he also removed all the pith Euler factor, and this lies in the same line. Okay. Now I move to the really normalized major Tate element. Okay, so I will write theta q zeta m is defined as follows. So sum runs over A, and which are elements in the Z mod MZ cross, and this normalized modular symbol, sigma A. And this lies in Q, color group, the group ring over Q. Q as joining Z mod M over Q, okay, here. And this is called the modular element. And this is the elliptical version of the Schelberger element. And we have two maps between the group rings. First one is a natural projection, and the other is the norm map. It's pi. It's the natural projection map is Q of Gauss group of Q as joining zeta ML Q to the group ring over Q of Gauss group Q as joining zeta just M over Q. This is just natural projection. And the converse direction, we have another map nu is the following map. So Q as joining zeta M here, but in the target, we'll have the bigger extension, Q as joining zeta ML over Q. So this guy needs a bit more explanation, but it's not very difficult to guess what it is. The sigma will maps to sum over tau, and where the taus come from is the pi tau is sigma. So in some sense, this guy is sum over liftings. And one proposition is a distribution relation for modular elements. So if I put the projection of this the major Tate element, then if L does not divide M, we have the following relation: AL times theta Q as joining zeta M minus nu and theta Q as joining zeta M divided by L if L divide them. And when L does not divide M, we have the following, still have the following relation. So AL minus sigma L inverse times theta Q as joining zeta M if L does not divide them. And proof is just using that Hacker relation. Okay. And one thing I need to emphasize okay, we only have the elements in the group ring over Q, but we need some integrability when we do your cell theory, or like to have the other arithmetic application. And one fact is that when the residual representation is irreducible, then, and good reduction, for example, then major Tate element, especially in the p-power direction, their modular element is integral. So if EP E bracket P as a Gauss representation is irreducible, and for example, the E has good reduction at P, then zeta Q as joining zeta P to the N lies in ZP of this Gauss group. So Q as joining ZP, zeta P to the N over Q. Yes, for all N. So these are the major Tate elements. And now using these elements, we can construct the periodic functions. So, okay. Periodic functions. Before moving to periodic function, any questions? I can just go ahead. Okay. And so, okay, so we go back to this three-term relation, and we want to modify this to have some certain norm-compatible sequence. So that's the process of P stabilization. Three-term relation to norm-compatible sequence. Is the P stabilization. In order to do this, we take a root of the Hecke polynomial. Take alpha, a root of x squared minus apx plus p, and consider the following element. Theta q as joining p to the n, but I put alpha here, is defined as follows. First, I divide by alpha to the n. And here, now I put usual major Tate element. We just constructed. So theta q zeta p to the n minus 1 over alpha times nu, and theta q as joining p to the n minus 1. Of course, yeah. In general, then this guy need not be integral, but when we consider the good ordinary reduction case, and if we take the alpha as a unit periodic unit root, then this is still integral. Anyway, if I put this, then this form a projective system. Which means like I just consider the projection in the higher power extension, p to the n plus 1, then we just have that alpha q adjoining zeta p to the n. Of course, right now I don't consider the integrality, and now I assume the alpha is a periodic unit. And which happens when it has a good ordinary reduction at p. Then theta alpha q adjoining p, all the p power root of unity is defined by the inverse limit following this relation of all the finite layer stuff, which lies in the ZP double bracket the Galois group of q adjoining all p power root of unity like this. And if I consider like a trivial type cumulant component, then we get the map to the Iwasawa algebra. And its image is the periodic function. This is how we get the periodic function. And okay. It remembers many properties, especially it remembers many L values. So interpolation formula. So if I evaluate this at the trivial character, set up p infinity, then I get the 1 minus 1 over alpha squared times theta q, which is the L value. And if I evaluate at the non-trivial character, non-trivial Dirichlet character, conductor p to the n, then the evaluation of chi is the 1 over alpha to the n and tau chi, and the twist to the L value, but the character is the inverse. So I consider the complex conjugation of chi. And here also the sign of the period, it depends on the chi minus 1. And this interpolation formula has also characterized this element. Okay, this is the construction of periodic function using modular symbols. And now I move to the algebraic side of Iwasawa theory. So Selma groups over the cyclotomic GP extension. Okay, so Q infinity is the cycloatomic GP extension of Q, and it's a Galois group. I denote gamma, and the Iwasawa algebra is GP double bracket gamma, as I said. And let me just recall the characteristic ideal. So M is the finitely generated torsion lambda module. Then M is pseudo-isomorphic to the following type of module. So F1 EI is all the direct sum. Because it is torsion, there is no free part. So I can write down like this. But like we allow the finite kernel and co-kernel. So this means like up to finite kernel and co-kernel. And all these Fi to the Ei so are determined by M. So characteristic ideal is product of all these divisors. So it's kind of the linear algebra over lambda. The Iwasawa algebra, which is not PID version of characteristic polynomial. Okay. So yeah, today I mainly will talk about the good ordinary reduction case. I just emphasize now. Okay, theorem. Kato. So A over Q and good ordinary reduction at P. Then also the the image of Gauss representation contains SL to ZP. Representation contains SL to ZP. In fact, conjugate of it. Then the Selma group, Q infinity of the P power torsion and its Pontryagin dual. In here, the Pontryagin dual means like a Hom ZP linear map from the Selma group to QP mod ZP is finitely generated torsion lambda module. And when E has the supersingular reduction of P, this theorem fails. So we need to introduce some sign Iwasawa theory to have a similar result. And so the Iwasawa main conjecture with periodic function due to major is the characteristic idea of Selma group is generated by the periodic function. That's good ordinary reduction of P. Then the ideal generated by periodic function is characteristic ideal of the dual sum group. Okay, in lambda. And what Kato proved is as I said before, in the large, when the image is large, then the one inclusion. So when the image Kato is large, which means like this, then this inclusion holds in lambda. But even without this image assumption, we still have the one inclusion, but after inverting P. Image assumption. This holds in lambda tensor QP. And the theorem of Skinner-Urban when there exists L exactly divide N, the conductor of elliptic curve, and the residual representation is ramified at L, then the opposite inclusion holds. Okay, so everything is about the good ordinary reduction case. And finally, I just want to also state the Mazur's control theorem. Still good ordinary case. So, P. Then we can see the behavior in the bottom from the top of the cyclotomic tower. So the natural restriction map lies in here, and if I take the gamma invariant, then has finite. Oh, sorry. Yes. Yeah, I was a bit too fast. Okay. And okay, so another question is there some fitting ideal version of this for more general extension? Yes. So, I mean, the general extension means, right, is for general abelian extension, there's a similar like conjectures due to Major and Tate, so-called the Major-Tate conjectures. In that case, yeah, many things like it's more, in some sense, difficult because as I said, one like a counterintuitive principle of Iwasawa theory is infinite extension is easier. One reason is the Iwasawa algebra has a very good structure. For example, all these like a characteristic ideal steps exist because the lambda is a very good ring. And if you consider just the finite extension, then that group ring is really horrible. It's really hard to like control. And of course, there is no good Iwasawa theory of finite layer group ring. And the only way to formulate the conjecture is to use the fitting ideal. And yeah, that's how it goes. EP ramified at L means like an EP as a multi-Figaro representation. Then okay, thank you. Okay, let me move. But yeah, if I'm too fast or if you have say something to me, just leave the message in the chat. Yeah, thank you very much. Okay, so this restriction map has finite kernel and co-kernel. Okay, now I can now I have some application of the Iwasawa main conjecture. So if the L value is 0, is equivalent to the evaluation of periodic L function at the trivial character is 0 by the interpolation formula. And this implies that using the Iwasawa main conjecture, the coinvariant, gamma coinvariant of the dual summer group is infinite. So cell Q infinity, EP infinity, and Pontryagin dual, and gamma coinvariant, which is same as the gamma. First, take the gamma invariant and taking dual. Is infinite. Then using the control theorem, the Selma group in the bottom is infinite. This is the one application of the Iwasawa main conjecture to a Birch and Swinnerton-Dyer type conjecture. And let me move to another. Let me move to another type of Birch and Swinnerton-Dyer conjecture. So-called the periodic BSD. And yeah, I do not consider so-called exceptional general in this case. I only consider good ordinary reduction. Reduction at P. The conjecture is as follows. So the rank of elliptic curve is same as, so my periodic L function lies in the one variable power series over ZP. So I can consider like its expansion at t equals 0. Then we can consider it's the order. So, or t equals 0 of LP. So it's similar to the original Birch and Swinnerton-Dyer conjecture, but I replace the complex L function by the periodic L function. Of course, their behavior is very different, but surprisingly, it is also expected. And in terms of the characters on Galois group, which means like the chi corresponds to the trivial character. And using the Kato's theorem, what we know is the one inequality. One corollary of Kato's theorem. Kato's theorem on the one divisibility of Iwasawa main conjecture is in all the setting of Kato's main conjecture, and Kato's result is the rank is bounded by the order of the vanishing order of the periodic L function. Okay, this is the result. And when you consider like a split multiplicative reduction, then you need to add 1. And in order to have this equality, what do we need? So what are needed to have equality in the periodic BSD? And first one is the equality of the Iwasawa main conjecture. The other is the finiteness of Shah. And this is also a non-trivial thing, is that I would not explain detail, but let me just state it. The non-degeneracy of periodic height pairing to have the periodic Birch and Swinnerton-Dyer conjecture. So this is the some applications of the Iwasawa conjecture. Okay, and now we go back to the Kato's elements. So from now on, what I want to do is I want to reconstruct the major Tate elements from the Kato's zeta element. From Kato's zeta elements to major Tate modular elements. Of major Tate. And I mainly follow the exposition of Kurihara. So basically, what do we do is up to now, what we've done is we start with the modular symbols. And from this, we built modular elements. And we construct the periodic L functions. And this is somewhat finite layer stuff. So this one requires P stabilization and plus taking the limit. And here I have my Kato's zeta elements. And I said, like, we can make the connection in the bottom is the modular symbol via dual exponential map. And also we can construct periodic L function using comma map. So comma map, in some sense, interpolate this dual exponential map. And in the middle, in the finite layer version of comma map, it exists. So this is in the middle. This is what I want to explain. Okay, so in order to consider this construction, we need to interpolate dual exponential a little bit in the finite layer. In order to do that, we first fix the p power roots of unity. A compatible system, of p power roots of unity. Primitive p nth roots of unity. And we need a very little of periodic Hodge theory. Little of periodic Hodge theory. So I consider like how can I say that is, I think let me just write down like this. So D is, if you know the periodic Hodge theory, it will be D drum of V. And from now on, I will assume it has a good reduction. And you don't have to worry about all the real periodic Hodge theory stuff, but what we need to know is that this guy is a filtered phi module. Filtered phi is a Frobenius. Or like you can identify these guys to drum cohomology of elliptic curve and crystalline cohomology together. So phi action comes from the crystalline homology, and the filtration comes from the drum homology. And filtration, using the filtration, I have this D0, and there exists the action of the Frobenius. And this is also drum homology. So in this filtration, D0 is indeed generated by the invariant differential, omega E. Invariant differential. So I regard D naught as a cotangent space of E, and considering the cup product pairing in the drum homology, then D quotient by D naught corresponds to tangent space of the elliptic curve. So let me write down the next page. So D naught is the cotangent space. And considering it's kind of dual, is the tangent space of E. As you've seen before, like there exists exponential map extending the formal exponential map. So the tensor QP adjoining zeta Pn plus 1 factors through D quotient by D naught, tensor the same field, goes to the cohomology, local cohomology, plus 1 V. This is the tangent space of E. And this map is called the dual exponential, sorry, it's just exponential map, and extending the formal exponential map. Okay. Then we consider a certain element in here. Yeah, it's a bit complicated formula appears because we really interpolate in the finite layer stuff. So consider an element, it's gamma naught, is the sum runs over 0 to n indexed by I. So Frobenius to I plus 1 is the acting on the invariant differential tensor zeta p to the n plus 1 minus I, and plus 1 minus phi inverse phi of phi n plus 2 power of the invariant differential. And this element lies in D tensor QP zeta P n plus 1. And the homomorphism, oh sorry, P n drum maybe nicer. Anywhere to be, yes, indeed. Here I assume it is crystalline because I don't want to like distinguish drum D cris and D drum. I just want to, yeah. And the homomorphism Pn starting from the local Galois cohomology, so QP adjoining zeta Pn plus 1, because I will like project down everything to the nth layer of the cyclotomic ZP extension. I put the n plus 1 here. Yes, that's the reason why I use the n+1 from here. The T is a Tate module. Sorry, it's the Tate module. To the QP is a group ring. Group ring is a Galois group of Q as joining P n+1 over Q like this. And this is the local Galois local Galois group and global Galois. Sorry, it's a I'm really confused. Local Galois group and global Galois group are identified because the P is totally ramified. Okay, that's what I want to say here. Okay, then A maps to the 1 over this certain pairing, so phi of omega E times omega E. Let me say this pairing is drawn. I will explain this pairing later. And sum runs over sigma. And sigma is the elements in this Galois group. It's pairing the exponential of gamma n. And the sigma acted on here and A. And this is the local Tate pairing times sigma. So we have the element in the group ring here, and now I explain this the pairing where then indeed we've already seen this pairing last time where just the drum from the tensor. Sorry, tensor QP as joining zeta P n+1 times as the pairing with the same thing goes to QP zeta n+1, and in the cohomology side we have H1 QP as joining it's the same roots of unity, and we have the same thing here. Goes to, but here I only have the QP. There is a difference, and this is a local Tate pairing, and this map is exponential. So gamma n lies in here, and exponential map of gamma n lies in here, and this is the dual exponential map, and it's not just the identification. There's a trace map. Then everything commutes, and that's how this pairing is defined. Okay, and the proposition is indeed the image of Pn is integral in the good situation. So the theorem is in Pn I put the correct zeta elements in this layer, then I will get the theta Q as joining zeta Pn+1, and project down to the trivial Teichmüller component. I get the theta Qn, and so we get the major Tate element. So this type of construction, I would call it the étale construction of the major Tate element. Okay, and also like in using the P stabilization and taking the limit, we will have the Kalman map. So there is Kalman map. Is call from the now we consider the Iwasawa cohomology. So QP goes to lambda. Oh, this means like the inverse limit with respect to co-restriction. So Q and P T is then this. In the good ordinary reduction case, if it is super singular, then we need to extend lambda, allowing like a growth condition, such that if I put like a localization at P of zeta element and taking Kalman map, and we recover the p-adial function. And another way to have the to consider the super singular case, and we have the signed Kalman maps to have the assigned p-adial functions. That's another way to consider super singular case. And how? So let me just say some words on the construction of the Kalman map. So how do we construct the Kalman maps? Instructions. So when we consider the elliptic curves or weight to modular forms, or weight to, then we can attach, I mean, elliptic curves itself is geometric object, and weight to modular forms, and we can attach the modular abelian varieties. Then we can consider explicit local points in there. This is, yeah, exposition. We can find the exposition due to Lubin, Kurihara, Kobayashi. Yeah, for example, you can check this explicit construction using by looking at these papers. And for the higher rate modular forms or general periodic representations, there's no such geometric object, then we need to use the periodic Hauss theory. So higher rate modular form or just general periodic representation, then we need to use the periodic Hauss theory. So-called, yeah, Perron-Lewis theory, Perron-Lewis local Iwasawa theory. These are the thing. I still have 10 minutes. Okay, I think we're almost done. So, yes. Now, let me just explain the Kato's main conjecture without p-adial functions and make the connection with the main conjecture with p-adial function, and let me finish it. So, Kato's main conjecture without p-adial functions. And okay, from the global duality, we have the following exact sequence from the global Gauss homology and taking the natural restriction map at P and quotient by its finite part. A finite part means like a local in the case of elliptic curve, this is nothing but EQP tensor ZP. And it goes to the Pontryagin dual of the Selma group. Now everything is on the bottom, just Q, not Q infinity. And it also goes to P-strict Selma groups. So also called the fine Selma groups. So this not means P-strict. And from here, we have the exponential map, a dual exponential map to the global differentials, which is nothing but the QP, generated by the invariant differential, one-dimensional QP vector space. And this ZQ, the Kato's element, lies in the L value times omega E. Yeah. Okay. And what we want to do is interpolate hold this picture over the cyclotomic tower. Tower Q infinity. Okay. And then ZQ infinity is nothing but the inverse limit of ZQN with respect to co-restriction. So Iwasawa cohomology, I have this. And in the good ordinary reduction case, then the Galois module, when we restrict to the local Galois module, then it splits. Sorry, it's not split. It is reducible. I should. Sorry about the misstatement. As GQP module, which means it's a reducible representation. So then taking the everything to the Q infinity tower, we have the following exact sequence. Indeed, it starts from 0. So Iwasawa, cohomology, QT, quotient by lambda times GQ infinity goes to H1, the local restriction map. Sorry, it's the everything is Iwasawa cohomology. Sorry. H1 QPT Iwasawa and quotient by from here, see H1 Iwasawa QP here T naught plus the image of a localization map, so lambda times local PZQ infinity. And it goes to, sorry, now my picture is broken a lot, but you will know what I meant. Here is nothing, there's no difference changing Q by Q infinity. And I have this exact sequence. And using Coleman map, and this is isomorphic to lambda quotient by the Piaget function. Okay, and indeed, Kato used his elements. What he proved is the one divisibility between these two, this guy and this guy. And using this sequence, he deduced the the main conjecture is the one divisibility between like a PIDL function and usual sum groups. So what Kato really did is when image is large, it means like an image contains SL to ZP, then the fine sum groups, P strict sum groups, is Pontryagin dual, is lambda cotortion. Sorry, lambda torsion. I already take the Pontryagin dual here. And the characteristic ideal of H1 Iwasawa cohomology quotient by ZQ infinity is contained in the characteristic ideal of this fine sum group. Okay, let me just write down like this. This is the theorem of Kato. Yeah, what Kato first proved using his elements. And one virtue of this formulation is this doesn't care about the reduction time. And the Kato's main conjecture asks you the equality of this, the inclusion. That's the Kato's main conjecture. Without PIDL function, there's no PIDL function in the both sides. And yeah, that's the everything I wanted to say today. And let me stop here. Thank you very much.
Thank you so much, Chano. Are there questions for the speaker?
Yep, please.
Yeah, so
there is a question by Meir.
Yeah.
how to
Meir, you can go ahead and ask.
Sorry.
so I think
Yeah.
I can.
I mean,
I have unmuted me, so please share your questions. Oh, maybe he has muted himself.
Okay,
Can you hear me?
yeah, I can hear you.
Yeah, you're audible.
I wanted to ask, is there any link between the PIDL function you constructed using measured rate elements and analytic PIDL function by Amis Velu and Vishik, those things using the H admissible distributions?
Yes. They are in the same, but it's like, yeah, it's.
Are they same?
Yes, I mean, they are. Yeah, they are basically the same, but like
up to some unit or kind of things.
Yeah. So, how can I explain that? So, in the modular symbol is construction is a kind of the. It shows all the finite layers in the Amis value type construction. That's how I understand.
So this construction is kind of pure algebraic, right? And the Amis value construction
I mean,
is analytic.
If you think modular symbol is algebraic, it's algebraic, but modular symbol is also analytic.
Yeah. Okay, thanks.
And okay, let me first give some answer in the chat.
Chat box, yeah.
So when you say this works for any reduction type, do we still assume big image? And in the result of Kato, yes, but like when you make a conjecture, of course, making a substitution or not, it's not very important. You can just ask a question. And when you like have the one-sided divisibility in this level, you need some big image assumption. And some good reference for studying PIDL functions in detail. I recommend like lecture note of Robert Pollack, and the title is the Overconvergent Modular Symbols, and it would help you to understand the construction of PIDL functions, especially in the modular symbol construction. Okay, and there are some a little bit. Give me a second. Okay. Yeah. Sorry. And okay, see another question. And what's the definition of the finite part in the prime? Y is equal to all right, this one. And yes, it's a very delicate question in some sense. So it depends on how you define the H1F, of course. And yeah, we can just define the HF as this. That's one way. Another way to consider is in the very general case, you need to use some decrease, and that it turns out they're all the same, but it's of course not like how not a direct, like not an immediate consequence. You need to think about that. But yeah, I mean, when I said this with elliptic curves, I really meant this. That's how I define. Yeah. And I think the Euler system methods are strong enough to get the final result for the Mahesh information at height 2 primes and about the height 2 prime ideals. I'm not perfectly sure how it works. Sorry, yeah. But for example, like in the USL theory, like one issue is about this higher chunk class type thing is a kind of a new invariant. So it is known as an error term in the USL theory, and I'm not sure how it can be applied to that thing.
I mean,
sorry.
Often we just localize at height 1 prime ideal and then work at
Yes.
prime ideal of the USL algebra. I was wondering if there's something finer one can do. I mean, after all, like these conjecture of Sharifi, Maculum, Sharifi, and Sharifi with cyclotomic units and so on, they seem to be finer, and also this Kurihara describing higher fitting ideals and so on. That those things also work with Euler system method. So
yes, about the Kurihara's result, I will make some comments at the end of the lecture if time permits. And yeah, about the height 2 prime ideals, I'm not perfectly sure what I can say. Yeah.
okay, thank you.
Can I just add something?
Yeah, sure.
Okay.
I mean, slightly tangential, but what Mahesh asked is Fine-Selmer group, like if you go a further extension, because it's a height 2 prime ideals, so they're supposed to become really small, and
Yeah.
the cell zero, again, sort of somewhat related to Maculum. They're supposed to become pseudo-null.
Yeah. And you're referring to Bloch-Kato Selmer groups. Yeah. For general, if you consider general Gauss representation, then we are assumed to use the Bloch-Kato Selmer groups. But in the case of elliptic curves, we can just use those Selmer groups, and they are same in this situation. Yes. And yes, the Robert Pollock selection. Yes. And
I think Sujata has a question.
She has raised her hand.
Okay.
Well, this question, I missed the lectures yesterday and the day before. So this is broadly to Mahesh and to Chanho. I tried to catch up, but the video quality was bad on the YouTube. And so I just looked at the notes quickly. No, this is a general question. So what I gather is the periodic L functions really works only after you drop the primes above P. This was something Mahesh also mentioned, right?
Mm-hmm.
But my question is, you can think of the periodic L function as a measure, right? So therefore,
Yes.
as a distribution, which really is a functional, so which gives you values when you take functions on G, let's say, where G is gamma or whatever. So how does, when you interpret the periodic L function in terms of functionals like this, then what role does dropping the primes above P play when you do that? Because then you're just scaling a function, isn't it? If you introduce the Euler factors, Euler factors, you're just scaling the function on the space of, let's say, CP valued functions or whatever. So,
Yeah.
so isn't the information enough for drop? Okay, suppose you have something after dropping the primes above S, then you automatically get information including the primes by just adding on the Euler factors, right? Or is there something more subtle that's going on there?
Yeah, I mean, yes. So okay, where do I start? Okay, so when we consider Kato-Zoro system does not remember Euler vectors at P, but when you take the Coleman map, and Coleman map recovers the Euler vectors at P in some sense. That's the one thing I want to say. And about I think this is related to the last question about the distribution measure. And like, if you just work with the modular symbols, then after evaluating all the modular symbols and taking the limit, then you get the periodic L function.
Yeah.
But like it's a kind of like if you first work with the modular symbols and deform it, then the so-called distribution value of the modular symbols, then just evaluating that, or so-called the overconversion modular symbols at 0 to I infinity, then we just recover the periodic function. That's the same thing in that sense.
So in other words, you really don't lose any information if you just consider periodic L functions. You can, if you consider the Euler factors, dropping the Euler factors.
Yeah, I don't think nothing is lost. Yeah. I mean, I think nothing is lost. Yeah, sorry. Yeah.
Okay, I have another question. This is not
please. Yeah.
This is not related to math. How are you lecturing like this, where you can see what you're writing on the page, and then how integrated with Zoom?
I mean, I use Zoom, and like I have some like a vertical shooting camera.
Oh, so you have
something like that. Yeah.
Which okay.
Yeah.
Okay, so it's almost a studio. Your study is a studio.
Kind of, yeah.
Okay.
My wife helps. Yeah.
Thanks, Chano. No, this is very convenient. I wish I could do this for my lectures.
Yeah.
So, yeah, great. Maybe there are some other questions or from the participants. Yeah. So if not, let's thank the speaker once again. Thank you, Chanho.
Thank you very much. Yeah.